Hello students, welcome back. Previously, we went through Fermat's theorem without the proof, just a statement of Fermat's theorem and its extension by Euler, along with some arithmetic background. The arithmetic background can be summarized in one sentence to this, basically. We can divide freely whenever we have non-zero integer, modulo p, which I'm highlighting in green. That's for prime, and in general, we need something a little bit stronger, relatively prime condition. And you can see this is a generalization of the previous, because for prime numbers are relatively prime to everything except for its own multiple. So this highlighted in green is, as a matter of fact, the same as blue for prime. In general, this is a little bit stronger. And then from those, you get Fermat's theorem. If P does not divide A, which is actually the same as this, A is non-zero mod prime. See that? That's why I'm using the same coloring. Then A to the P minus 1 power is congruent to 1, modulo P. Also, you can do this as well. A to the P power is congruent to A mod P. Multiplying A to both left hand side and right hand side, we're going to get that. And then this P minus 1, let's pay attention to that. I'm highlighting it in purple. Let's pay attention to that. That turns out to be the same as phi of m, the number of positive integers less than m that are relatively prime to m. And if m is a prime number, then you're going to get p minus 1, because everything is okay. 1, 2, 3, 4, all the way up to p minus 1. Everything is okay. In general, if you have a composite number, not everything, you're going to have some factors of m, and also there are some positive integers that share some prime factors with m. In those cases, we have to screen those out. And then the condition here is, let's use the same coloring, blue, the relatively prime condition again. So we can summarize kind of like this. For Fermat's original, which works for modulo prime, we have A to the P minus 1 power is congruent to 1 most of the time. In general, A to the P power is congruent to A. And then Euler-Fermat, this is an extension of the first line. Okay, before proving it, let's go ahead with an example problem. Let's see, how about these examples? Determine A to the 103 power mod 13. Looks like this is sufficient because 13 is a prime number. So how do you work out A to the 103 power? Well, please remember A to the 12th power is congruent to 1 mod 13. So if I can express this as A to the some 12q plus r like this, then that's congruent to, no, that's equal to A to the 12th power times the quotient q times A to the r power. Now let's use congruent notation, and that's congruent to A to the r power. That's what we're going to use. Let's put some space in between. Okay, there you go. That looks better. Yes, some space in between. Okay, all right. So what is this quotient and what is this remainder? Well, let's see. 12 times 96 times 8 is 96. Yeah, 96 is probably the closest. Okay, all right. So this is 12 times, oops, 8 times 12 plus 7 if you use the division algorithm. So 8 to the 12th power to the 8th power. That's all become 1. And this is the 7th power. So you're going to get 8 to the 7th power. That's a lot easier computation, but 8 to the 7th power, and that's not the computation you want to do. Is there any way to reduce it further? 2 to the 3rd power to the 7th power. So that's 21st power. That's, let's see, 13th power. So 2 to the 13th power is 1. And then 2 to the 8th power? Yeah, okay, that's what we're getting. And 13th power is 1. 2 to the 8th power and 2 to the 8th power. It's not too bad. 2 to the 8th power, 2 to the... Okay, alright, I give up towards 2 to the 8th power. You can do it by paper and pencil computation, but yeah, 256. And then divide by 13. So... Okay, alright. Let's see. That's what I'm getting. The answer is 9. Is everything okay? Oh, excuse me. What am I doing? What am I doing? Not 13th power, 12th power. So this is 9th power. So 9th power. So we have 5. Still, I like it up to here, but up to 2 to the 9th power. And then is there anywhere further to simplify it without going to calculator here? Let's see, 2 to the 9th power. 9th power. Can I reduce it further? 2 to the 2nd power is 4. 2 to the 3rd power is 8. 2 to the 4th power is 16. That's 3. Mod 13. So 2 to the 9th power is 2 to the 4th power times 2 to the 4th power times 2. So that's 3 times 3 times 2. Okay, all right. Yeah, this is a kind of computation we can handle. And then 9 times 2, so that's 18. And that's 5. Mod 13. Okay, all right. Okay, all right. So in the end, we get 5. So here, previously, I cheated with mathematical computation, but now, all right. I did everything with just traditional computation, as if I were a person living in 18th century, learning these kind of things. Let's see, what did I do in my answer key? Yeah, it's the same thing, 8 to the 7th power. How do you handle 8 to the 7th power? Oh, okay, all right. I did a little bit differently. 8 is reduced to -5. -5 squared is positive 25, and that's -1. Because 13 times 2 is 26. Okay, we have a bunch of -1s. Oh, okay, this computation looks simpler to me. But if you miss that and then you got off the 2 to the 9th power, yeah, you can handle with that as well. Okay, all right. Okay, in any case, answer is 5. Still, it's much better than calculating 8 to the 103 power, especially if you had been living in 18th, 19th century. How about the next problem? Wow, this looks worse. Oh, no, actually no, it's easier. This looks really intimidating, but no. Let's see. We have mod 11, and 11 minus 1 is 10. Therefore, 2 to the 10th power is congruent to 1 mod 11. And then getting multiple of 10 is actually easy. Previously, mod 13, so we had to do some work, but mod 11 is actually much easier. 11 minus 1 is 10, and 10 is an easy number to do any kind of mental math. So I put this one into 0, and then 3rd power, decompose it out, and then 10th power to something, that's all going to disappear, and we just have 8. So we're going to get 8 minus 1, 7. So this is going to be congruent to 7. Yeah. So mod 11 is much easier. Even though this number looked much bigger, no problem. Let's see, how about these? Oh, looks like these are problem that's using Euler's extension of Fermat's theorem, because as you can see, we have a composite number here, another composite number there. So looks like this is a good time to stop, and then let's work out part C and part D in a separate video. We didn't do the proof yet, but we went through a couple of exercises regarding Fermat's theorem. As for Fermat's theorem, yeah, that's what we are doing basically. Okay, let's stop here. See you soon with next example problems.